Hello friends, welcome to my YouTube channel. It is my first educational video on YouTube. Here we will discuss about the engineering subjects. Today we are going to discuss on the deformation in metal forming. Our question is explain deformation and their types with the example. First of all, we will start with the definition. Deformation occurs when body is subjected to an external force where the applied force can be tensile or compressive. On the basis of deforming nature, material deformation can be of two types. First is elastic deformation and second is plastic deformation. Elastic deformation is a reversible process which deforms when the external force applied on the body and regain its original shape and size when the force is removed within the elastic limit. In this type of deformation, atoms are displaced from their equilibrium position by stretching and bending of the atomic bonds. To maintain the constant volume of the body, linear strain is accompanied by the lateral strain. Further, we can divide elastic deformation in two ways based on their behavior. First is linear elastic deformation, second is non-linear elastic deformation. Linear elastic deformation obeys Hooke's law, which says that stress is directly proportional to strain, and the proportionality constant is called Young's modulus of elasticity, which is denoted by capital E. Stress is equals to external force per unit cross-sectional area. Strain is defined as the ratio of change in shape to the original shape. Elastic modulus based on the material and their deforming nature. It is called linear because its strain is approximate to 1. Now, second is non-linear elastic deformation, which are described by the scalar function. Designing of these deformation is done by tangent and secant modulus. This graph shows non-linear behavior of the material. In this, tangent modulus is the slope of the curve at some specified value, and secant modulus is the slope drawn from the origin to some point of the curve. Now, talking about the mathematical relation and their significance. Elastic moduli measures separation of bonds and the material stiffness. Second is, larger the elastic modulus, higher will be the material stiffness, which makes deformation more complicated. Third is, these elastic modulus are function of the interatomic forces, distances between them, the structure of the atom, and their orientation. Now, the next significance is elastic moduli is slightly decreases with the increase in temperature. Poisson's ratio is defined as the ratio of lateral strain to the linear strain. Next significance is shear modulus. It is defined as the ratio of shear stress to the shear strain. Moving to the next significance, bulk modulus or volumetric modulus of elasticity is the ratio of mean stress to the volumetric strain, which is given by K is equals to sigma m upon delta. In conclusion, all moduli are related to the Poisson's ratio, which is given by G equals to E divided by 2 bracket 1 plus V, or K is equals to sigma m upon delta, which is further equal to E divided by 3 in bracket 1 minus 2V. Now, talking about the example of the elastic materials are rubber, glass, ductile materials, etc. This rubber is more elastic than the glass is more elastic than the copper, and copper is more elastic than the steel. Now, talking about the stress strain curve for a ductile material, it shows a graphical representation of a material behavior when it is subjected to a load or force. The standard unit of stress is pounds per square inch or newtons per meter square, and the strain is unitless. Graph shows a straight line between 0 and point A, which is called proportionality limit. Hooke's law follows up to point A, and the region under this curve is called the resilience. As an example, springs are designed at proportionality limit. Stress beyond this limit causes non-linear elastic deformation up to the point B, which is called elastic limit. Beyond elastic limit, material experiences plastic deformation and yielding start at the upper yield point, that is point C, till the point D, which is called lower yield point. The region between upper yield point and the ultimate strength point, that is point E, is strain hardening region. Material gain their strength during strain hardening. From the ultimate strength to the fracture point F, necking occurs in the material without applying further stress. At point F, material fails due to the shear stress at 45 degree with vertical. This is a cup cone failure and the process is called necking. Further discussing about the second type of deformation, that is plastic deformation, it occurs when the force is applied beyond the yield strength. During this deformation, both elastic strain and plastic strain occurs in the body, but only plastic strain remains in the body after removing the load. There are two mechanisms involved in the plastic deformation. First is slip and second is twinning. In slip mechanism, blocks of crystal slide over one another along the crystallography planes, which is called slip planes. During this mechanism, each atom moves equal distance along the slip plane, which produces a step, but the orientation of the crystal remains the same. These two diagrams show slip mechanism and the tuning mechanism. Tuning is the second mechanism of the plastic deformation, which causes change in the plane orientation. It also helps to slip further. In this mechanism, displacement of the atoms occurs due to shear force, and the tuning portion of the crystal is mirror image of the parent crystal. Moving to the relations in plastic deformation. Due to the complexity of plastic deformation, there have been many stress-strain relations proposed. Here, stress is the function of strain hardening exponent, strain rate, sensitivity, time, microstructure of the material. Now, relation in plastic deformation are as follows. First one is sigma equals to k into epsilon to the power n. Second one is sigma equals to k into epsilon to the power m. Third one is sigma equals to sigma naught plus k into epsilon to the power n. And fourth one is sigma equals to k in bracket epsilon naught plus epsilon whole to the power n. Now, small n is the strain hardening exponent whose values vary from 0.1 to 0.5. The second one is strain rate sensitivity whose values varies from 0.4 to 0.9. Sigma naught is the yield strain and the epsilon naught is the strain from previous work. Simple example of a plastic deformation is a wet chewing gum, which can be stretched dozens of times to its original shape. Thank you for visiting my channel. If you have any suggestions, please comment below.